So, let us start with a definition. Definition of the multiplicity of an eigenvalue. Definition of maybe let me put it in a bracket, the word algebraic multiplicity of an eigenvalue. So, let T be a linear operator on a finite dimensional vector space V, which has say dimension n, of dimension n. And let lambda naught be a eigenvector corresponding to, or lambda naught be an eigenvalue of our linear operator T. So, let lambda naught be an eigenvalue of T. Then the multiplicity of lambda naught is the largest positive integer such that lambda minus lambda naught divides the lambda minus lambda naught to the power k divides the characteristic polynomial of T. So, let me define the multiplicity, maybe let me just write a bracket algebra. So, it is also many times also called algebraic multiplicity. The algebraic multiplicity of lambda naught is the largest positive integer k such that lambda minus lambda naught to the power k divides the characteristic polynomial f of lambda of T. So, let us go back and look at our examples earlier. So, the first example, the characteristic polynomial is lambda minus 2 the whole square. The only eigenvalue here is 2 and the algebraic multiplicity of the eigenvalue 2 here is equal to 2. The same is the case with example 2, where the characteristic polynomial is the same. Okay, how about example 3? Example 3 has the characteristic polynomial given by lambda minus 2 the whole square times lambda minus 3. There are two eigenvalues, namely lambda naught equal to 2 and lambda naught equal to 3. There are two different eigenvalues here. The multiplicity of the eigenvalue 3 is equal to 1, that is the largest number such that lambda minus 3 to the power k divides our f of lambda. And similarly, the algebraic multiplicity of the eigenvalue 2 is equal to 2. Okay, so why are we concerned about this? The next theorem tells us that the algebraic multiplicity always dominates the dimension of the corresponding eigenspace. So, let me prove that theorem for you. So, let T be a linear operator on a finite dimensional vector space V, and suppose let lambda naught be an eigenvalue of T. So, the theorem tells us that then dimension of E lambda naught is less than or equal to the multiplicity. So, I will slowly drop the adjective algebraic. So, let us just call it multiplicity of lambda naught. So, notice that if lambda naught is an eigenvalue of t, then there exists at least one vector which is non-zero and such that it is the eigenvector corresponding to lambda naught. So, therefore, the dimension is certainly greater than or equal to 1. This theorem tells us that the dimension has to be less than or equal to the multiplicity of lambda naught. So, let us give a proof of this. So, the fact that so let us give these things names. So, let k be equal to dimension of E lambda naught, and therefore, what does that mean? Then there exists V1 to Vk such that V1 to Vk, or rather which is a basis of E lambda. So, this is a basis of the eigenspace E lambda naught corresponding to lambda naught. Each of the V1, V2 up to Vk are eigenvectors with eigenvalue lambda naught, but any linearly independent set is contained in a basis. So, we can extend it. So, extending this we get a basis which is given by say V1 to Vk, which are eigenvectors, and then Vk plus 1 to Vn, where n is the dimension of our vector space. We will slowly stop putting n as being the dimension of V. I will always assume that n is the dimension of V in the entire lecture. Okay. So, let us try to look at how the matrix of T. So, let us call this beta. So, interested in what is T beta beta, what is the matrix of T with respect to the basis beta. What will be the first column? The first column will be T V1, and notice that T V1 is just lambda naught times V1, and similarly T V2 is lambda naught times V2. So, the other bases do not contribute anything. So, I would say that the first k columns will just have a lambda naught times I k, and here there will be a 0, the 0 matrix, which is basically n minus k cross k a matrix. And then there will be some matrix here which I would like to split as something into k cross n minus k matrix C, and a B which is n minus k cross n minus k matrix. Okay, so what will be the characteristic polynomial of T? So, let us see. Then the characteristic polynomial of T is given by, so recall that the characteristic polynomial of a matrix is invariant under similarity, and therefore, characteristic polynomial of a linear operator can be defined with respect to any basis. So, what is this? This is basically a determinant of T beta beta minus lambda times I n, which will just turn out to be equal to the determinant of the matrix lambda naught minus lambda times I k. The 0 and the C are untouched, and there will be a B minus lambda times I n minus k. This is precisely how the characteristic polynomial will behave. By one of the exercises which was done in week 6, this is just going to be equal to the determinant of lambda naught minus lambda to the power times I k times the determinant of B minus lambda I n minus k, the determinant of block matrices. Recall that this is a block matrix of the correct sizes, which was written a bit above here. Yes. Okay. So, what is the determinant of lambda naught minus lambda times I k? That is just going to be equal to lambda naught minus lambda to the power k times some g of lambda, where g of lambda is the polynomial of degree n minus k, which is basically the characteristic polynomial of B here. So, it is going to be a polynomial of degree at most n minus k, and therefore, this is so what does this mean? This means that k lambda minus lambda naught to the power k. So, hence, so what is this? This was f of lambda, and we have that f of lambda is lambda naught minus lambda to the power k times g of lambda. Therefore, lambda minus lambda naught to the power k divides f of lambda. But what was the multiplicity of a given eigenvalue? It is the largest positive integer such that it is the largest positive integer L such that lambda minus lambda naught to the power L divides f of lambda, and therefore, k has to be less than or equal to the multiplicity of lambda naught. But what was k? K was nothing but the dimension of the eigenspace, and this is less than or equal to the multiplicity of lambda naught, and we have completed the proof. So, let me just show you the theorem we have just proved. We have just shown that if you start off with a linear operator and let lambda naught be an eigenvalue of the given linear operator T, then the multiplicity of the eigenvalue always bounds the dimension of the eigenspace. So, in the previous example we saw that when the dimension was equal to the multiplicity, our linear operator was diagonalizable. If the characteristic polynomial splits, and if this inequality which are circled in green, if that turns out to be an equality, then we had that, of course, we already know that it was no, we found out that it was diagonalizable by explicitly computing a basis consisting of eigenvectors. So, that as I have already noted, that tempts us to conjecture that if in a general n cross n matrix, if we can somehow show that if we are given that the dimension of the eigenspace is indeed equal to the multiplicity, then for all the eigenvalues lambda I, then maybe our linear operator is diagonalizable, and that is true, and our next goal would be to exactly prove that. So, let us gather some of the statements needed to prove what we just mentioned. So, the first one is a statement which we have already proved in another guise. So, let T be a linear operator on a finite dimensional vector space V. So, let lambda 1 to lambda k be distinct eigenvalues of T. Suppose V I, and suppose V I belong to E lambda I. So, that means V I's are elements in the or vectors in the eigenspace corresponding to lambda I. If we have that V 1 plus V 2 plus up to say V k. So, this is for I equal to 1 to k. So, for each of these we have V i's in E lambda s. So, suppose V 1 V 2 up to V k all add up to the 0 vector, then Vi is equal to necessarily equal to the 0 vector. So, I have slowly stopped bothering about whether it is clear from the context as to the 0 being written is the vector 0 or the scalar 0. I think by now you should be able to quickly catch from the context itself. So, you should carefully look at what the context is and conclude whether our vector is the 0 vector or whether the 0 is the 0 vector or the 0 scalar. So, here it is the 0 vector, as you can see. So, I will leave this as an exercise to you. We have already noted that if lambda 1, lambda 2 up to lambda k are eigenvalues and distinct eigenvalues, and V1, V2 up to Vk are corresponding eigenvectors, then they are linearly independent. You should use that to conclude that this forces Vix to be equal to be the 0 vector. Okay, so I will leave that as an exercise for you, and let me now make a next maybe theorem. So, let lambda 1, lambda 2 up to lambda k be eigenvalues of distinct eigenvalues of a linear operator T, and suppose we get hold of a set say S1 which are consisting of eigenvectors with eigenvalue lambda 1, and suppose S1 is linearly independent, and suppose S2 is a similar set corresponding to lambda 2. So, if we look at lambda 1 union lambda 2, the question is it again linearly independent? The answer is yes. In fact, for each lambda I, if we can have such an Si consisting of linearly independent vectors of which are eigenvectors corresponding to lambda I, then the union will be a linearly independent set. So, let me write it down. So, let T be a linear operator, or maybe I should just consider matrices and the same. So, linear operators on V, so linear operator on V, and suppose and lambda 1 to lambda k be distinct eigenvalues of T. Notice that I have always carefully written lambda 1 to lambda k. K could be strictly less than n. There needn't be n distinct eigenvalues. If it is having n distinct eigenvalues, then we already know that it is diagonalizable and we do not need to do any of these things. So, in fact, the interesting case comes when k is strictly less than n in whatever we are doing right now. So, if suppose we get hold of Sj be a linearly independent set consisting of eigenvectors with eigenvalue lambda j, then S equal to S1 union S2 union Sk is linearly independent. So, let us prove this result. So, let each of these Sj's, let us give some names to the vectors in each of the Sj. So, let Sj be given by Vj1, Vj2 up to Vj n subscript j. Each of the Sj's consists of such vectors. So, we would like to show that the union is linearly independent. So, let there be a linear combination of these vectors which is equal to the 0 vector. So, let Aij be such that summation A, okay, I j might not be a good idea. So, let us be a little careful with indices. So, let me use yeah, that is okay. J is going from 1 to k and say I is going from 1 to n subscript j, and suppose a I j v, maybe I should okay, that is okay, v j I, okay, I should have just called it as I and it would have been nice, but that is okay. Well, let us call it AGI, does not matter, AJI, VJI. So, I goes from 1 to Ni and so on. Okay, this being equal to the 0 vector. So, this is a linear combination. A typical linear combination will be like this, and we would like to show that each of the coefficients AJI are 0, right. To do that, what we will do is we will define Wj to be equal to summation I is equal to 1 to Nj AJI VJI. So, notice that J is fixed and we are looking at the thing in the bracket here. This is what we are focusing on, and we are looking at the sum here. What can we say about Wj? Each of the Vji belongs to Sji. So, this means that Sj rather, this means that Wj belongs to span of Sj, which is contained in E lambda j, right. Why is this? Since Sj Wj belongs to span of Sj and Sj is contained in E lambda j. Because of this, each of the Wj's belong to E lambda j, and this expression above also summation j goes from 1 to k, I goes from 1 to nj of AJI Vji is now equal to summation j is equal to 1 to k Wj. That is precisely what we have written it as, and we are given that this is equal to the 0 vector. But the previous proposition tells us that if we have V1, V2 up to Vk are eigenvectors corresponding to, or rather elements vectors in the eigenspace corresponding to lambda 1 up to lambda k, then each of them have to be necessarily 0. By the previous proposition, we have Wj is equal to 0 for all j. But then what is Wj? Let us get back to what our Wj was. Wj was the expression which I have put in a box, and this implies, so let me write it down, this implies summation AJI Wji Vji, where I goes from 1 to Nj is equal to the 0 vector. But what do we know about Sj? We know that Sj is a linearly independent set. So, there cannot be a linear combination of vectors in Sj which is equal to 0. This implies that, so for all j, this implies that Aj I is equal to 0, the scalar 0 for all j and for all I, and hence S is linearly independent, because we took an arbitrary linear combination to be the 0 vector, and we notice that this forces each of the coefficients to be equal to 0. So, yes, this is a linearly independent set. Okay. Now, let us state the main theorem. Main theorem states that if we have a linear operator T, and suppose the eigen value is lambda 1 up to lambda k, it satisfies the condition that the dimension of the eigen space. So, suppose the characteristic polynomial of the linear operator splits. So we are given all this. So suppose we are in the situation when the characteristic polynomial of our given linear operator splits, then our linear operator is diagonalizable if and only if the eigenspace, the dimension of the eigenspace of each of the lambda i's, each of the eigenvalues is equal to the multiplicity of the eigenvalues. So let me state the theorem. So let T, again let T be a linear operator on a finite dimensional vector space V. Such that the characteristic polynomial of T splits. So recall that that was the entire context. We know that if T is diagonalizable, the characteristic polynomial splits. We are now studying that given that the characteristic polynomial splits, when can we say that our linear operator T is diagonalizable? So then T is diagonalizable if and only if the multiplicity, if the dimension of E lambda I is equal to the algebraic multiplicity of E lambda I, multiplicity, I got it wrong, multiplicity of lambda I for each eigenvalue lambda I of T. So notice that it is an if and only if statement. It says that if T is diagonalizable, then the dimension is the same, and if the dimensions are equal, then T is diagonalizable. So let us prove both the directions. So let us first assume that T is diagonalizable. Assume that T is diagonalizable. We would like to show that the dimension of E lambda I is equal to the multiplicity for each of the eigenvalues lambda I. So what does it mean to say that T is diagonalizable? So let beta be a basis of V consisting of eigenvectors of T. Beta be a basis of V consisting of eigenvectors of T. Okay, so let us do one thing, let us start the proof one line ahead and let n be equal to the dimension of V. Let us call the dimension of V to be equal to n. Okay. So, and lambda 1 to lambda k be eigenvalues of T. So, there are k distinct eigenvalues. So, let me just add the word distinct. There are k distinct eigenvalues of T, k is less than or equal to n. Okay, that is an exercise for you to show that there cannot be more than n distinct eigenvalues of a linear operator T. Okay, so we have a basis beta and let beta I be equal to beta intersected with E lambda I. So, beta I captures those eigenvectors in beta corresponding to lambda I. Okay, so let and Ni be equal to the number of elements in beta I. Now, Ni is the number of linearly independent vectors which are eigenvectors corresponding to lambda I, right, and The first observation is that Ni has to be less than or equal to the dimension of E lambda I. So, let us give E lambda dimension of E lambda I is some name. So, let Ni well di be equal to the dimension of E lambda I and mi be equal to multiplicity of lambda I. So, we know a few things. We know that di is by previous theorem or by a previous theorem, not the penultimate theorem. We have di is less than or equal to mi, and the fact that beta I consists of linearly independent eigenvectors corresponding to lambda I implies that, and the above observation and the fact, let me write down the reason, the fact that linearly independent set in a vector space of dimension di has size less than or at most Ti. This implies that Ni is less than or equal to Di. But we know a few things about Ni, namely that summation Ni, notice that summation Ni is equal to n, because summation Ni is the number of vectors in beta, which is the basis or which is a basis of V, and therefore, this is equal to n. Since beta is a basis. Also, what is summation mi? That has to be equal to the degree of f of lambda, the characteristic polynomial, which is equal to n. This is from the explicit form of the characteristic polynomial we have seen in the last week. And what do we hence have? We have that n is equal to summation ni, which is less than or equal to summation di, which is less than or equal to summation mi, is again equal to n. So, there is a sandwiching that has happened, and therefore, summation mi, or let me put it this way, yeah, mi minus di is equal to 0, but we know that mi minus di is greater than or equal to 0 by one of the previous theorems. Even if one of them is greater than 0, the sum cannot be equal to 0, because each are non-negative quantities for all I. This implies both star implies mi minus di is equal to 0, and hence we have proved one side of the result for all I. So, what have we proved? We have proved that if we assume that T is diagonalizable, then we have shown that the dimension is equal to the multiplicity. Let us now prove that the dimension of E lambda I equal to the multiplicity forces our linear operator to be diagonalizable. Okay, so let us now assume that mi is, or rather di, which is less than or equal to mi, is in this case equal to mi for all I. So, what does this mean? This means that the dimension of lambda i's, sorry, dimension of E lambda i's is equal to the multiplicity. That is what it means. So, let us do one thing. Let beta I, so let beta I be a basis of E lambda I. We know that beta I has size di, and by the previous theorem, beta is equal to beta 1 union beta 2 union up to beta k. This is linearly independent, because they are linearly independent sets in different eigenspaces, and therefore beta equal to beta 1 plus beta 1 union beta 2 up to beta k are linearly independent. But what is the size of beta? But size of beta, notice that each of the beta i's are mutually disjoint, is equal to the summation of the size of beta I, which is equal to the summation of di, but this is now equal to the summation of mi, which is equal to n. Therefore, we have a linearly independent set which has size equal to the dimension of V, and that forces it to be a spanning set and hence a basis. Hence, beta is a basis. What is beta? Beta consists only of eigenvectors of T, and therefore, basis consisting of eigenvectors of T. Hence, T is diagonalizable. So, we have obtained a necessary and sufficient condition on when T is diagonalizable, given that the characteristic polynomial splits.